Testing, testing, 1, 2, 3, testing, testing. Now everybody knows what kind of phone I have. An old one. Testing, testing, 1, 2, 3, testing, testing. Okay, that's working. Boy, the quality is decidedly bad today, eh? Good lord. I guess that's what we get for deciding to start these things at peak hours, eh? Well, at any rate. Nothing to be done about it. I've actually I considered for a while, like, tinkering with the time that the streams happen, because from one perspective, it technically shouldn't make any difference. But it's better to sort of keep things the way the registrar set them up, I think, by and large, only change things when absolutely necessary. I'm asked how my day was. Pretty all right. It was a nice day outside, and I didn't get to work in the garden. I had too much indoor work to do, so that's kind of a bummer, but otherwise, I'm hoping tomorrow's a nice day and maybe I can weed the carrots or something. So, everybody logging in now. Ho-ho. I have a bit of a small announcement to make regarding due dates for this course. Yes, good morning. The assignment 3, which originally I had intended to be due Sunday at midnight, it was pointed out to me by a person over my email that it is perhaps unreasonably cruel of me to put the midterm, the first test and the assignment within 24 hours of each other being due. So, with respect to that, I have graciously stepped down off of my golden throne in my castle made of clouds and decided, thou shalt receive a 1-day extension for thine assignment 3. So the assignment 3 will be due 24 hours after it was originally intended to be due, which isn't a big extension. The problem with this course in the summer schedule is that we've got like one assignment per week, and if we start to let them pile up, that's not good either. And the assignments are actually more work than the test is, so. And that's your hint for the test for today. No more hints for the test. Just kidding. We'll probably have more test hints today. Yes. Good. I'm looking forward to the weather tomorrow then. I have a question from MN, the mysterious figure. Will today's material be on the test? No. Today's material will not be on the test. Test 1 is comprised of the material on topics 1 through 4. And this topic and the stuff for this week and next week will be, that'll be applicable to test 2. So that's what you can expect there. You're welcome, Taylor. So, yeah, that's the announcement. Oh, and this extension is applied also to assignment 5. Like and subscribe. No, what was it? Yes, assignment 5 is extended in the same manner. Assignment 5 occurs, basically it was designed the same way as the test 1 assignment 3 relationship, except 2 weeks into the future. So it makes sense to have both of those shifted by 1 day. So, collective or individual, I'm not sure what that is in reference to. So, when you ask me questions in the chat, please make sure you include the context, because there's such a time delay between me reading what you're writing and you commenting on what I'm on it. And if that's a follow-up question, please include the what I was talking about, because I will have forgotten, because I have a brain that is very all around and about. I have a question. I'm assuming there will be no Piazza help during the test. You're assuming incorrectly, actually. So one of the problems that we have during a distributed test of this nature is that there's really no replacement for this idea of, I want to raise my hand and ask the teacher a clarifying question about a particular question that's on the test or something like that. I'm going to see. Pardon me. So let me finish this question. So basically, the Piazza forum will be your, I want to ask the TA or the professor a question. We very strictly would request that nobody post any part or whole solutions to test questions that they're working on to the Piazza forum, or anywhere else for that matter. Cue thunderous, ominous lightning in the background. And if like stuff like, oh, I noticed this test case seems to not work. Maybe this test case is wrong. We'll have an avenue to tell you, no, the test case is right. But anyway, so there we go. So Piazza will be available to help. Basil will be on that. I will also chip in occasionally. I'll keep an eye on things. So the likes, do we need to like, or just one like per hint? Well, let's see how many likes we're up to, and maybe that will be... Oh, I can't see that from here? Good lord. Can I see it from here? 16, so 16 hints. I don't know, this is gonna be, this is gonna get out of proportion very quickly. However, just sort of in the general context of all of this stuff, thank you. I think that it would be useful right now to have a sort of a quick Q&A session with respect to anybody having any tests. It's sort of already been happening already, but if anybody has any questions pertaining to the test that's upcoming, please voice those now, and I will answer them in the first part of this lecture. No sense in making the people who watch this afterwards wait for it, eh? Well, maybe there is. Maybe we want to punish them. No, let's not punish people. Basil is a legend, I agree. Will the test be harder than usual as it is online? We will have more time. It depends on what you mean by... it depends on what you mean by harder than usual. I would say that the test is roughly in line with... I don't know. It's probably, in terms of length, I sort of was shooting for around the length of the exam from last semester, which I know I just said the word exam, but no, I ended up making test 3 entirely too long, so I sort of rolled things back a little. My idea is that the test should take you about 2 hours to complete. However, given the amount of disparity there tends to exist between programming skill with respect to individual students in the class, it's usually more of a, shotgun approach to test time than anything else. So, harder than usual? I don't think so. The questions themselves, I'd say the difficulty of them sort of caps out at about what you'd see on one of the more difficult assignment questions. But, You'll just have to wait and see. Will I be able to fetch the test on Jupyter, or is it on Avenue? From confused, well, confused. No longer shall you be confused, because you will be able to get the test from both sources. Is the test similar in length to assignment 2? No, it's shorter. When we're writing full-out exam on Saturday. You guys are so you guys do have a assignment on, like, have we double booked? Is there another test? If everybody who has a test on Saturday, this Saturday coming, could you please, like, say I have one in the chat so I can get a gauging of how many people this is actually relevant to? How many questions on the test? I think it's 7. Give me a second. No, it's 6. Pardon me. There are 6 questions on the test, and I'm not going to tell you what they are or what they're worth. Will the test require us to use specific types of loops, for versus while loops, for example? Well, Python programming does not require you to use specific loops, for versus while loops. Like, from the perspective of the autograder, there's really no way to tell, right? Those types of details are not, they can't be picked up, so we can't mark for them, so we're not going to require you to use them one versus the other. Generally speaking, you should use whichever type of loop you think makes the most sense for the context in which you're using it and the level of skill you have with that type of loop. So the test will not require you to use specific loops. Would the test/exam include test cases as well, in the same format as the assignments? Yes, sir. Yes, sir. The test upcoming, each question has a between 2 and 4 visible test cases which you can use to check your answers, and there are a number of hidden test cases that are used to mark. It's in the same format as the assignments. Are there built-in test cases, or do you have to make your own? They're built-in. You can, of course, and are encouraged to make your own test cases. You know, if you feel that the visible test cases which you're given do not adequately describe all of the functionality which you wish to test, then absolutely, please write yourself some visible test cases, and that will be cool. Will there be hidden test cases? Yes, that's how we grade the assignments. Are we getting bonus question? You are getting a bonus question, a single bonus question. Okay, I know I said I wouldn't tell you what the questions were out of, but the maximum grade on the test at this point in time, which I'm done the final version of it, so this will be the final grade, the final maximum score is 42 out of 36. So the bonus question, you can infer how much it's worth from that. Yes, so the test is going to be administered. It is a Jupyter notebook. If that wasn't clear before, let me make that perfectly clear. All of the assessments in this course are Jupyter notebooks, which will be submitted to us via the same channel as the assignments. So the mechanism that you are used to for filling out and submitting your assignments using Jupyter, whether that be through a local installation of Jupyter or accessing our JHub2 server, that is what you will use to submit your test. Are there bonus questions on the test? I already answered that. Do we have to do the test in one sitting? It does not matter in what manner you do the test. You may consider this, basically the model that I'm going for here is an open book test. So there are certain things which are permitted. Basically, the time restriction comes from the difference between the test being released and it being due. We absolutely will not accept any submissions whatsoever past the due date. So make sure, double check that your assessments have been submitted. And, if you want to, I know it says it on that one Piazza post not to double submit, but if you are worried about it for this particular instance, we can wink at it. But don't tell Swale I said that. So, with respect to that, no, you don't have to write it all in one sitting. There's no like program inside of Jupyter that'll like grab your computer and say, you must finish this test before you exit this window. Nothing like that. However, so permitted things that you can do. You're welcome to look at the Python documentation. You're welcome to look at other sort of online resources that may help you through specific coding problems with the code that you're having. Things like Stack Exchange. Like, I can't remember how a for loop works. You can look it up. You can also refer to my lectures that we're doing right now. You can refer to the lecture slides. All of these are permitted aids. What is not permitted is for any single piece of the code that you submit to not be your own work. It's got to be your own work. And you also are required not to share your answers with anyone. Do not copy, do not paste. No. We'll be watching you. So, if we are good with the assignments, will the test be fine with as well with respect to the level of difficulty? I have a question. Yes. If you're doing well on the assignments, then you probably don't have anything to worry about for the test. I always say probably because, everybody's different. Do the test functions function the same way as the assignment in the sense that our last submission is the one that's marked? Yes. The same rules apply with respect to test submission as assignment submission. Thank you. That's a really easy voice. How do you actually check feedback after clicking Fetch Feedback on Jupyter? I'm not actually sure because I don't think I've ever done that with like Student View. But if you want your feedback emailed to you, then send an email to Swale. He's one of the TAs. You can find his email address on the syllabus. So, anywho, if that is everything that everybody has to ask us about, oh, I'm sorry, I missed a question. Do we need to handle exceptions, or can we presume that that input is always valid? We haven't actually covered exceptions yet. Testing in exceptions, I believe, is topic 7. So, no, I'm not testing you on exceptions. Let me just take a look and make sure there are no other questions that I missed here. Okay, so, my goodness. So, without further ado, I think we will move on to our actual lecture material for today. Today we are going to be talking about functions and recursion. So, this is an important set of slides to understand. So, I should address the topic of recursion somewhat. It's a difficult concept. Another question about the test. Can we import stuffs? Yes, you can use libraries. You shouldn't have to use many of them, but generally speaking, my approach to solutions to problems is I don't care how you get to the correct answer as long as you get to the correct answer, so long as you didn't cheat. So if you have some clever little trick that I haven't taught in the course that makes your code a lot more efficient, by all means use it. I'm not requiring, I don't want to require people just to use the syntactic constructs and semantic constructs that we've discussed here in class, because if I were to do that, I would be severely limiting your creativity. Post-traumatic programming disorder. So, yeah. So, oh, there you go. Anyway, back to recursion. I kind of, personally, I am not completely convinced that recursion has a firm foothold as a topic that should be in a first-year programming course. I'm just going to lay it out flat. This is real talk. Recursion is a reasonably difficult concept with respect to your brain meats. It takes a familiarity with programming. Like, to understand it, you have to understand programming at a level that is probably beyond where most of you are right now if this is the first time you're doing programming. However, I have to cover it. I have to cover it because it's in the calendar description for this course. So, like, insofar as there is curriculum which is given to us university professors, it mostly consists of that calendar description, actually. That and, like, legacy material. We're actually at pretty high liberty to, put courses together as we see fit, so long as we're covering the stuff that's in the calendar description. Although, there's obviously, like, concerns with respect to the courses that lead on from courses. But anyway, recursion is a hard topic, and we're going to do our best with it. I'm going to try to explain it as well as I can, and if you don't get it, then maybe you can rewatch the section that does the section of the lecture in which we talk about recursion. But there are also some neat things with respect to functions that we're going to talk about as well. Some neat stuff that you can do with them. And there's some good examples, like some good programming examples in this lecture set as well. So anyway, today we're going to talk about functions, scoping, software design, recursion, and searching, and functions and as an object. Is it possible to learn this power? Yes. Okay, everybody who's a COMPSCI major and did Haskell. Okay, sure. But 1JC3, I'm willing to bet a lot of you were feeling like you were being thrown into the deep end. It's a concept that derives more from the world of formal mathematics than it does from the world of, like, the normal development and progress of computers, if that makes sense. Like, with respect to, like, the Turing Machine became the dominant model for computation, but there were other models, right? One of the other models on which Haskell and the idea of recursion is based is called Lambda Calculus, and we're going to be talking about lambdas today. But it's kind of like, it's very math. Like, the whole thing is very math. You'll see what I mean when I say that very shortly. So, functions. Functions were originally a way of grouping together sequences of operations under a common name so that it could be referred to multiple times later on. This bears a lot of similarity to the old programming idea of the subroutine. The best way to think of it is as an abstraction mechanism. So, when we talk in regular speech, there are. Can I get something for you? Okay. when we talk in regular speech, it's not necessary to describe every aspect of an apple. You can just use the word apple. Apple is a stand-in for all of the things that an apple is. Functions, in the same way, are a stand-in, like a function name is a stand-in for all of the operations that a function is declared as having. However, as time progressed, this sort of morphed into the idea that it should be a bit more similar to conventional mathematics. So the idea of the subroutine sort of eventually polymorphed into the idea of the mathematical function as applied in programming. So, that's why you have stuff like cosine, sine, logarithms, all of these things. These are functions, right? But yeah. And incidentally, arguments were an innovation at one point. So, anyway, this will be review, but this is how you declare a function. You've got the def, which is used to define the function. That's the keyword. You then put the name of the function, a comma delimited list of input arguments, 0 or more variable names which will be assigned to whatever values the function caller provides. The body of the function and the return statement have to be indented. Very important. Indentation is key. And the output of the function is given in a return statement. This should all be review. This should also be review. We have a difference in nomenclature between the comma delimited list, that is, comma separated list of variable names delimited by round parentheses. Those are our formal parameters. So the parameters that are declared with the function itself, those are formal. Very formal. They are wearing suits and ties and tuxedos and monocles. And they go to fancy dress balls. The actual parameters are much more realistic. So in the actual program execution, you have actual variables that hold actual values. And when you pass those actual variables into the function that has been declared formally, those parameters are the actual parameters. And just to remind everybody of this, in Python, we use pass by assignment. So there's an implicit step between the calling of the function and the executing of the instructions that are in the function. There's an implicit assignment of the actual parameters to the formal parameters. This is an assignment statement, so it includes all of the implications of the assignment statement that we have been dealing with so far, including stuff with respect to aliasing, which we were discussing in the last topic. Yes. Another term for calling a function is function invocation, like you're invoking a, sacred right of an elder god, or something like that. Something sufficiently Lovecraftian. Invocation. That's another important word. So, some of you may have noticed, as you've been programming in Python, that sometimes functions, especially the ones in the libraries, are somewhat inconsistent in the number of arguments that they take. And, for example, it's a very quick example of this. If we remember our range function, right? Not that. Jeez. So this thing does different things depending on how many arguments are assigned, right? Pardon me. Just so we can see it. The way that it accomplishes this is Well, it's the technical term for it is polymorphism. Polymorphism is the idea that a function can be called in different manners and mean different things depending on the manner in which it's been called. As opposed to a lot of languages, like if a language lacks polymorphism, what that means is that if it's called in a manner that's not appropriate, then it'll, crash out on an error in some way, produce some unexpected result. So, you may have noticed that if you, the humble programmer, the humble 1MD3 student, try to just leave out one of the parameters for a function that you've written, for example, let's say we had a function def add3 takes x, y, and z, very simple example, return x plus y plus z, and if you tried to add 3, 2, and 5, you'll see we got a type error. Add 3 missing one required positional argument z. So it complains. It gives us an exception. It says, ugh, you're missing an argument. So you can actually make it so that it does not require all of the arguments it's given. If inside of the function definition you give it an assignment statement, it's not really an assignment statement. It's assigning a default parameter. But you can assign a default parameter so that if the function is called with fewer parameters than it would normally need to be fully specified, it can just imply what the missing one is from the default value that you provided. This is a very cool thing. A number of different, library functions that you're used to have this type of functionality built in, hidden away, and the only way to learn about it is to read the documentation. Use the source, Luke. So, yeah, so that's a default parameter. You can see that another way of assigning things inside of the call, you can actually refer to the name of the default parameter specifically. So, if you... There we go. And z equals 12. It's kind of silly, because you can also just do that. However, what this allows you to do, I think, is it allows you to address any of the parameters that you might want to have a particular... Oh, let's make it so that the output is different, shall we? Good grief. Yeah, so if you have a long list of optional parameters, Python can infer them positionally, right? So if you provide 2 and don't specify, it'll just provide the first 2. However, if you want to skip over one and assign a parameter that's out of order, then what you can do is you can just address that one specifically using the name of the formal parameter. Hopefully that makes some degree of sense. So, yes, that is how to use a default parameter. Yep. So that's how that works. Hopefully that's sufficiently clear to everybody. If you have any questions, please let me know in the chat. So, let's talk about 360 no-scoping, by which I mean scope. That's a joke for all of my friends who had an internet connection back in 2012, when they used to talk about 360 no-scoping. Or maybe I'm being uncharitable. Maybe that was only 2015. Anyway, it was a while ago. Go away. So, when you define a variable, that variable is defined within certain contexts. There are contexts in which it exists and contexts in which it does not exist. When you create variables, it's important to understand the scope of that variable. So, generally speaking, and this is kind of like your, intro to programming version of scoping. I can go into it in a little bit more detail than this, but generally speaking, you've got global variables and you've got local variables. So the idea is, within the context of a Python script, any variable that's used or assigned within the regular execution of the Python script, that is not inside of a function, this is of global scope. Global variables are accessible inside of all contexts of the file. Sometimes this can be problematic. We'll get into that a little bit later. A local variable is local to a specific context. A function is a context. A class, when we get into classes, a class is also a context. Gotcha. Oh, the kitten wanted to see what I was doing. Say hello to everybody on the live stream today, little kitten. Smooshy, smooshy. Yeah, she's getting big. Her tail is getting very poofy. Whoop. Yeah. Okay. I know. So when a variable is in a local scope, the best way of thinking about it is that it exists within that scope and it does not exist outside of that scope. So when you declare a variable inside of a function, then you once that function is finished, the variable disappears. It's no longer available. I believe I've already talked about this at, I think we already went over scope a little bit, but we've got some examples. So, she came right up to me. If the kitten comes right up to me while I'm streaming, I have to grab the cat. So anyway, the big brain, I'm a super programmer way of thinking about scope is basically to understand that when you're executing a Python script, you're executing the same type of thing as a function, right? So you can think of a function as a subroutine, right? We start getting into ideas like the system call stack. The system call stack tells you what part of what program is currently being executed, right? And we're going to get into the idea of call stacks a little bit because it's relevant to the idea of recursion. But when you call a function, there's a register inside of your CPU that says, okay, I am now inside of this function. And then after that, there's another function, another. Basically, it keeps track of all of the programs and subprograms that are currently running. And of course, a lot of people don't think about computers this way, but your function is executing inside of the context of your Python script. Your Python script is executing within the context of your Windows PowerShell. Your Windows PowerShell is operating within the context of your operating system. Your operating system is operating inside of the context of the kernel, and the kernel is operating inside of the context of the underlying hardware. So, everything is in layers. And scoping really refers to the particular layer that you're on. So another way of saying this might be, instead of global variables, variables which are scoped to the script I'm currently executing, and local variables might be variables which are scoped to the function that I'm currently executing, but that takes too long to say, so we call them global and local variables. But this is a good analogy, though, because you can imagine if you have functions which are defined within functions, which are defined within functions, which is totally a thing that you can do in Python, then the scoping behaves in the same way. If you have a function within the function, variables which you declare within the inner function are local to that inner function, and variables declared in the outer function are global across everything inside of the function, including any function definitions which occur inside of that original function, which I know is a very weird way of saying it. Let's see here. Let's see what we can't do. This is it. This is happening, folks. This is MS Paint time with your lovable and affable professor. So if you have a script, yeah. So this is a script, yeah? And within that script, I've got a function, right? And it's got a definition, etc. Within that function, I might have another function, right? Which you might have another definition right there. So if I have three variables, x, y, and z, then x is global to everything inside of the script context, y is global to everything inside of this context, and z is global to everything inside of this context. However, with respect to the larger program, y does not exist outside of its scope, and z does not exist outside of its scope. So you could easily do something like x equals y. So yeah. I have a comment. So essentially, scoping is like making tiers of different accessibility. That is exactly, precisely, 100% what is going on. Yes, it's actually it's a data management policy. The problem that you have is, try to imagine, if you will, a Mad Maxian world where any piece of data inside of a computer could be accessed by any program running on that computer. There would be no such thing as data privacy of any kind. And, you can argue that, privacy doesn't exist because we're on the internet. But that's not the case at all. If you need a password to log into your account, the reason for that is that if you don't have your password, if you don't have the password, you can't get what's in the account. So if you're a program that's using variables, the variables are not accessible outside of that program, unless you declare them as such. And, there are specific ways of doing that, but generally speaking, yeah. Anyway, so let's talk about the specific examples that we have in the slides. So this is just a regular computation with no functions involved. You can, oh my goodness. With respect to be every statement in the program after its declaration, or including its declaration if you want to include it. Doesn't really make any semantic difference. So with respect to this program, the scope is everything, and x, it's everything except n. So we can't access x before x has been declared. We get our familiar error where you can't access, you can't read something before you write to it, So all of this code is at the quote-unquote top level of our program. As a LaTeX person, that makes me sad. I'm going to have a talk to them about their quotations. So once this code is run, we can't call it again with a different input. There's no reuse, there's no modularity, and all the variables are global. This is, Oh, what? Oh my goodness. How much did we lose? Okay. This is an imperfect thing that is occurring over an imperfect medium. Okay, so what was I doing 5 minutes ago? Okay, Jesus. 2 minutes, 1 minute tops, just the slide. Okay. Yeah, I see that business in MS Paint got through okay. 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 All right, I'll just go over the slide again then. It's not, actually I took longer for it than it deserved. So, you can consider the scope of a variable within the top level of a program to be everything past the point of declaration for that variable, at least in imperative languages where the order things happen in matters. Believe it or not, there are programming languages like that, but that's beyond the scope of this course. So, with respect to this, n has a scope of everything past the declaration of n. X has the scope of everything past the declaration of x. We can't, therefore, call x within n, because this would violate causality fundamentally. You can't have the effect of something before the cause. You can't read something before it's been written to. And practically, if you try it, you'll get your exception, right? There's a variable not assigned exception or something like that if you try. So, with respect to a function, in this case, the factorial example that we've been talking about for a while now, the scope of the scope of x, for example, within the factorial function is everything inside of the factorial function past the declaration. Oh, yeah, I didn't even get that. So everything past the x is within scope for x, so x can be and is used inside that scope. Notice it's giving you one more line here. The reason that it's doing that is to indicate that if you wanted to add more lines to the function, then you could. So with respect to the scope of I, this slide claims that I is scoped inside of the for loop in which it exists. However, I think I've tested this before, and that doesn't actually hold water, that claim. Let me just see if I can duplicate it. For let's say, oh, not again. Ugh, this is terrible. We're good? Okay. Looks like we're good. Okay. So be it. So the definition itself is in the top level of the code, as are these print statements. This means that you can use the factorial function within the context of the entire file. But here's one for you. If you define a function within another function, that new function is scoped to the function that it's declared in, so it's not accessible outside of it. Generally speaking, we consider these to be helper functions. In fact, we often call them helper because they are just another way of, helping a function out with a little bit more abstraction power. That's if there's anything that the entire the entire course of human history has taught us, it's that the power lies in the hands of the best abstraction. So, in this particular further example, oh shoot, I'm running into the break. Okay, we're going to call it here for, well, I don't know. I'm going to go for 3 more minutes. We got a lot of ground to cover today, and I want to get through it all. So, give me 3 more minutes, guys. So, obviously, with respect to this factorial example, if you attempt to print x or n outside of this factorial function, you will find that they can't be accessed outside of that function because they're local to the function. I'm pretty sure I've already demonstrated this in No, don't do that. Oh, no. Oh, shoot. No. Come on. Boop. Sorry. I clicked on a thing that I shouldn't have clicked on. It's not ready. It's not ready for the world to see. My goodness. Good grief. Sorry about that, folks. Maybe I'll show you that to you a little later, but that's not. This icon is a personal project that I'm working on, and I accidentally clicked it, and it's not ready for the world. Anyway. So, if you have some q equaling 7 out here and you run that, then q obviously does not exist outside of that scope, and it'll trip an error. That's the main thing. So yes. So you can also do with this with global variables. If, for example, you have this variable n is equal to 6, and you if you have that parameter included inside of your function, it will refer to whatever 6 is in your your top level execution. There are several problems with this. For one thing, it constrains where your function can be called, right? If your function is called before n has been assigned, then you're going to run into that same error. And, that might be asking your user to keep track of too much extraneous detail. But anyway, let's call the break here, and we will resume class at 6:30. it's hilarious because I actually have started leaving myself a little sticky note to indicate that the microphone is off, and I just completely ignored my own sticky note that I left there specifically for the purpose of reminding me not to forget that my microphone was off. Yeah, I know. I know! So frustrating. Good lord. So, anyway, to your question, can you explain how to make a function do different things depending on the number of actual parameters, like how range x is range 0, but yeah, like the range thing? Short answer, no. Long answer, no, and I'm very sorry. I don't know how to do that. Unfortunately, I'm not what you might consider an expert Python user. Which, if you look in the documentation, you'll probably find something like that. Sorry, dude. Anyway, so we were just talking about why the global variables are universally terrible. They're not universally terrible, but they're pretty bad. The problem is that when you use a lot of global variables, what you're in essence doing is you're complexifying the situation. Like you're throwing away a lot of the useful properties that come along with modularization through abstraction. And, you can do so, but at your own risk. And that risk is not being able to understand what the heck your code is doing, which, believe me, is a real problem that happens to real people that might even be giving live streams right now. So anyway, n in this example is a global variable. Even though it isn't defined when we define the function, n is defined by the time we run the first function factorial. So this is a difference between Python and other things that you might have, other programming languages that you might use at some point. Python is an interpreted language. This means that it is never actually compiled. This means that when you are running a Python script, it doesn't go through it beforehand and say, you got a syntax error right there. It actually tells you what the syntax errors are, etc. When you hit the thing that you're trying to execute. Or maybe semantic errors. Maybe it does. That's a good test. Let's see. Can we not? So if I introduce a syntax error right there, but if we print before that, do we actually get the print statement? We do not. Okay, so it scans ahead for syntax errors, but all of the exceptions that would be raised, such as, like, basically a lot of things that would have been loaded onto preprocessor errors in other languages, such as not like using variables before they're being declared, or use variables out of scope. These are things that Python has decided to load into its runtime error system rather than its compiler error system, because it doesn't have a compiler. So what that means is it does not identify n as being used out of scope, because it waits until it hits n and then decides if it's out of scope or not, which means that this actually requires an execution of the factorial function in order to actually work. But, that's maybe a bit of an academic difference. So the thing about global variables, they may be read outside of, they may be read inside functions, but in order to use them inside of a function, this is a slightly different situation. So if we actually try to, do this, replicate this, something interesting happens. So let's imagine that we have a global variable q. We want to assign it to some value. And whoop, there we go. There we go. What happens? That works. No, it doesn't. Q is 7. Haha, I need to delete this line. Do I? So you'll notice that even though, so it doesn't work, even though we have assigned q to the value of 7, we've called this function, which sets q to 10, despite the fact that we are doing this, q remains 7 when we try to output it down here. So the question is, what gives? What the heck, man? And it depends on the manner, the thing you're doing. Sometimes it'll just ignore the statement. Sometimes it will actually crash out on an actual error. Functions can't. Oh, actually, you know what? If I change it, okay, I just figured it out. If you change this to something that requires simultaneous read and write, then you get an unbound local error, which is the thing. Local variable q referenced before assignment. So it still thinks it's local, right? Basically, it's okay to have variables which are named the same things inside of different scopes. So if we go back to our stupid little MS Paint thing, if you have, for example, 3 variables, all named Z, right? Inside of these 3 different scopes, if you access the variable Z in each of these scopes, it'll access the version of Z which is in the most local scope. So if you access Z down here, you'll get this one. If you access Z here, you'll get this one. And if you access Z here, you guessed it, you get this one. So basically, when you do this, you're creating a local version of Q that is assigned the value of 10 and then promptly ignored. And that actually does not conflict with the global version of Q, which is in the larger context. However, it doesn't affect it either. So you can do whatever you want with the locally scoped Q. It has no effect on the globally scoped one. So the question becomes, how do we break stuff out of that scope? How do we permit assignment of global variables inside of local contexts? Perhaps there is a situation in which this could be useful. The answer is you declare it at the top. You use the keyword global. You declare the name of the variable, and then you are permitted to use it as if it were a global variable, including writing. You can kind of think of it as like giving yourself a file permission. You know, if you have a file that's like a read-only file, and you go into the properties and change it so that you can you give yourself write permission on that file. This is basically the same thing, but with a variable rather than a file. So if we do that and then we print, you can see we get 10, which is the updated value of Q. This is, there you go. If it's a variable, what is the benefit of naming different things the same variable? Maybe you just have so many variables that you forget what the names of them all are. That's totally a thing that happens. Like, why not name it something else and not have the confusion? You totally could, but again, you might not remember all of the variable names. It might also make sense that the same thing means different things in different contexts. Yeah, hopefully that's something approximating an answer. I do agree. It's better to not have things conflict whenever possible, but, you know, think of this as another tool in your tool belt. So, you have to be careful with side effects. So, all my Haskell crowd are like, side effects? Who needs those? So, generally speaking, when you use global variables, what you're doing is you're allowing communication outside the normal channels. And communication outside of the normal channels might be a very good thing. You might be able to write more efficient code that way, or come up with some clever solution to a problem you're having. The problem is that you quickly complexify things to the point where you don't necessarily know how things are operating anymore. You can imagine that if you have a program that's running for a long time and everything is making all kinds of modifications to global memory, you're not necessarily you might get yourself into unexpected states. And generally speaking, we don't like unexpected things when programming. So yeah, just be careful with them. Generally speaking, the best thing to do is to have everything communicate through the input, have it communicate through the parameters of the function and return statements. That's usually the best thing. Anyway, that concludes our scoping topic. So let's move on to the idea of software design. This is kind of the fluffy bit before we get into recursion. So, I've talked about these ideas before, but generally speaking, when you are writing functions, when you are creating modular programs, think about like Lego, right? Ideally, you want your functions to fit together like Lego pieces. You want to be able to take a programming problem, and break it down into its constituent parts, right? You want to be able to say, okay, for this part, I need to do X, Y, and Z. I have functions that do X, Y, and I have another function that does Z. So to do X, Y, and Z, all I have to do is take the output of X and Y and run it into the input of Z, and then take the output of Z and run it through and call that my output. You know, you want to take the problem, right? And you want to divide it into smaller chunks. Divide it into as many small chunks as you possibly can, and then solve those chunks individually, and then compose a solution from the chunks that you've solved. Believe it or not, this is what you're doing a lot of the time when you're using a loop. When you're using a loop, what you're doing is you're saying, okay, I have recognized that this particular thing can be solved if I go one by one through the elements of a list or some similar situation. That is a decomposition. You have decomposed it and you have abstracted it. This is the type of thing we like to see. So functions that are being written according to these principles are reasonably self-contained. That means minimizing the use of global variables, generally. They achieve a clear purpose. Every function should have one thing it does and do that thing well. And a function should be able to be reused, because otherwise, why would you need one, right? So, because of this principle of abstraction, because when we write a function, we are essentially operating on a relationship between inputs and outputs. That means that the program can be used without having any knowledge whatsoever of how it achieves that result. And this is key. It does not require any knowledge of a function's inner workings in order to use that function. all you need to know about that function is the relationship that it provides between inputs and outputs. So think, for example, about the sine function. You don't know how a computer computes sine. I don't know how a computer computes sine. I don't need to know how a computer computes sine. All I need to know is that if I give it a value in radians, it'll give me the sine of that value if I call the sine function. This is what we're talking about. So, in the context of larger programs, you can have many different functions, especially if you're programming in Haskell, because it's a functional language and everything is a function. Even literals are considered functions of 0 arguments. So each function should be a relatively small and designed to do only one thing. This is especially true in large programs. Just because the program's large doesn't mean that functions need to be large as well. Or at least, not all of them. Some of the functions are obviously going to be larger because, it's a larger program, but, you can have large functions use smaller functions that use smaller functions. You can arrange hierarchies of functions. It's wonderful. So, an example of this is Twitter. So, in Twitter, you have a function which stores a new tweet into the database. You would also have a function to record a user liking a tweet. You would also have a function to delete a user's tweet from the database, if they really delete it, etc., etc., etc. Yes. Some people think that Twitter is scary. I don't. Twitter is just a database. It's the people using the database that are scary. Anyway, so there's a cool thing you can do with functions in order to provide information about the function to people who might want to use it. This is called the docstring. So the way that you create a docstring, it's very, very simple. You select the line underneath the function definition, and you enter 3 quotation marks. This is a docstring. You basically type stuff up like you would type a comment, put 3 quotes ahead of it, 3 quotes behind it, and it becomes a docstring. And one of the cool things that you can do is if you call the help function, which is a thing that you should all know about now, on any particular function, it will give you both the definition of that function, i.e. what the arguments it expects are, and it gives you whatever the docstring is. This is extremely useful. You can do this with anything. See print, this print function that we've been using all over the place. Notice that it has all kinds of default parameters that you never knew about, right? It also has descriptions on how to use it. Use the help function. There you go. Sum. Return the sum of the start value plus iterable number of numbers. There you go. So did you know that if you sum a range from 0 to 10, and then you start it off at 100, that actually does, that has an effect. Ta-da! So yeah, there you go. Docstrings. So generally speaking, there are a few things that you want to see inside of the documentation to a function, right? This docstring that I wrote for add3, this is a terrible docstring. Not only does it not provide a description of what the function does, it also does not describe the outputs or the inputs. What you're mostly concerned with when people are reading your docstrings is you are concerned with, what do I put into this thing and what do I get out of it? right? So that's the information that you want to provide to the user. You want to provide any assumptions, requirements, or preconditions for what the input must satisfy in order for it to work correctly. So, for example, you might think, oh my goodness, this stupid little adding function that we've written, that can't possibly have any assumptions attached to it, right? Wrong. Assumes all inputs are, well, not even necessarily integers, but numerical. Or even assumes all inputs are defined for the operation addition. Can I use that? Does that work? It doesn't, yeah. Octothorpe. I just want to see if the quotes are going to come through. Yep, they do. So, like, for the example, if you really wanted to, you could and are of the same type. So it also doesn't have to be all on one line. You can split it onto multiple lines and it'll still work fine. There you go. So, for example, you can, with add 3, enter 1, 2, 3, right? Because concatenation is also a thing that's defined by using the plus thing, or plus operator. So you can see it produces a string, so that's fine. However, if you start mixing them, you'll start running into issues. So basically, if there's some way that the user can configure the inputs to your function in such a manner that the function breaks, that's a good thing to include in the documentation, generally speaking. You don't necessarily want to say, this thing will break if you do X, because that seems kind of passive-aggressive. But whatever the thing that breaks it is, come up with a condition where that should never happen, and then put that in the documentation. So, and of course, you want to give the user some idea of what the output's going to do, right? You want to give them some idea of what the relationship of the output is to the input. So that's also a good thing. So, for example, if y'all remember our making change function that we were writing at the end of last topic, we have the documentation string assumes target is an integer and that coins is a sequence of integers in decreasing order. Returns a dictionary with a key for each entry in coins and a corresponding integer for the number of coins of that denomination. That's a good doc string. So, and of course, as I've already mentioned, the help function exists. Help can be used to access documentation from any function you can think of, as long as it's got a doc string. And if it's something that's in one of the Python libraries, you can be reasonably assured that in order for them to have published it as a library, the documentation has to be up to a certain standard at least, and that will include doc strings, because this is the way that Python likes to do that. Different languages will have vastly different ways of approaching the problem of documentation. This is definitely more specific to Python. But, you know, this is a Python course, fundamentally. Well, we teach Python. We'll leave it at that. Anyway, let's talk about the nitty-gritty, the meat and potatoes. Let's talk recursion. So, you might be asking, what is all the fuss about? Could he just tell me what recursion is already? This thing that he's been building up since like an hour and a half ago. Oh my goodness. So, A recursive function is a function that calls itself. And that's it's a lot harder in practice than it is to sort of say. But yeah, a recursive function is a function that calls itself. So let's talk about factorial. This is an example that we've been doing. We haven't seen it in a little while. So you may notice in the definition of factorial, we actually are using factorial to define factorial. This is a recursive definition, because in this definition, factorial is defined by further uses of factorial. I've got a couple of questions. In what case would you want to use docstrings rather than using comments? When you want your comments to be applied to the function itself rather than the stuff that's occurring inside the function. So if you're documenting the uses of a function, then you use a docstring. I'm guessing for when you want public info and private developer info. Yep, that's another one. That's a reasonable way of putting it. So, recursive definitions always include, well, sometimes they can get to be pretty strange beasts, but for our purposes, a recursive definition consists of a base case and an iterative case. So the purpose, the mathematical need that recursion is filling is the idea of the, you better not walk on my grass. Okay, the kid totally did walk on the grass, but not the part that's like the new grass that can't be stepped on, so I guess that's okay. Even though, technically a violation of the rules implied by the fact that my grass is still roped off. People and their children. When I have children, they'll be much better behaved. Anyway. Factorials work on what's called an inductive structure. So if you've ever delved into the arena of mathematical proof, you've got basically two forms of mathematical proof. You know, this is a very simplistic view, but there are basically two ways of creating mathematical proof. Well, I'll include a third, but it's irrelevant at the moment. You've got deduction, and you've got induction. So in deduction, it's like Sherlock Holmes. You've got all of these rules, and you've got all of these premises, and using the rules to transform the premises, you reach some conclusion. Hey man, I know I'm old. Yes, definitely. Also, the grass is really like long and thick at this point, and probably quite interesting and pleasant to walk on. But you know, I should just mow it already. But you gotta give it a chance, man. Anyway, so in deductive proof, you've got a system of reasoning and premises, and you try to reach a conclusion. It's basically the same way that like logic and rationalism works. In an inductive argument is a very specific type of argument. You start off with a quote-unquote base case. If I were to explain it like in words rather than math, it would be something like the grass is alive. right? So the grass is alive is a statement. The inductive case would be something like, if the grass was alive yesterday, and then the grass is alive today, right? That would be like the simplest form. So if you can prove that the grass was alive at some point in history, and you can prove the fact that if the grass was alive yesterday, then it is alive today, regardless of what days that is, regardless of what days those are, you can always, you can prove that at every point in the future the grass is still going to be alive. That is the essence of a inductive proof. Sherlock actually used inductive reasoning in my argumentation prof. I'd be ashamed if I didn't point out literally any chance I get. Yeah, okay. Well, I know, but that's the meme about Sherlock Holmes, right? It's like, deduction, my good Watson, deduction. It's like, Mr. Sherlock Holmes, what are you doing with your tax return? Deductions, Watson, deductions. Anyway, there's also proof by contradiction and proof by construction and other types of proofs, but this is already a long lecture. So anyway, mathematically speaking, the way that we express this in Python is we have a call to the function that's being defined recursively inside of that function. Cool. The reason this works is that, well, it's mimicking the inductive structure. So if you have, well, you know what? I'm getting a little bit ahead of the slides, so I'm just going to let the slides play out. So notice the correspondence here between the base case and the iterative case in both the definition and in our Python representation. If n is equal to 0, give it 1. Otherwise, if n is greater than 0, n times n minus 1 factorial, return 1, return n times factorial n minus 1. So the thing that happens when the program execution hits this recursive step, this recursive call to factorial, it goes back up to the top and continues until it hits it again and again and again and again, until it hits a case where it doesn't have to call itself again, and then everything just collapses down and you get an answer. So here is an example with the factorial with some print statements so that you can see a bit more what's going on with it, right? So, and most particularly, you can see the order in which things are occurring. So at the top, we have entered factorial with n is equal to whatever n was. When we are about to return 1, about to return from base case, and when we are about to, or actually just after the call to factorial, about to return from iterative case in n that's cut off. I need to talk to these guys about the slides. So, if we call factorial with 5, enters factorial with 5, 4, 3, 2, 1, and 0. 0 is returned from base case. These should be comments. Or this should be differentiated from the rest of it because it's syntax highlighting. About to return from base case, about to return from iterative case in n is equal to 1, 2, 3, 4, 5. So, essentially, you can imagine what's going on here in the same manner as this that we were talking about before. You've got a version of factorial running at the top level. That one invokes another version of factorial, which invokes another one for n is equal to 3, 2, 1, and 0. That's because each one of these depends on the step that comes after. This last one, because it's the base case, that does not depend on anything coming after it, so there's no further versions of factorial which are invoked. It returns its value to the next level, which returns it to the next level, which returns it to the next level, etc., until it is finally returned to the top level. And all of these additions or multiplications are combined to form the final result. So this one would be calculating 5 factorial, 4 factorial, 3 factorial. Ordinarily, I'd do this on a chalkboard, but since, you know, limitations being what they are, I don't know, this is kind of the cheap and dirty way of doing it. So that's roughly the structure. So, comment, I definitely see myself accidentally getting stuck in infinite loops with this, lol. Yes! They're a little more kind than infinite loops, though, because they do eventually kind of, like, if you forget to do the base case, or you don't do the base case correctly, then what happens is eventually Python runs out of space for more function calls, like the function pointer, the function stack just runs out of room, and it exits you on an exception right there. It might take a while depending on what you're doing, but that's kind of how it works. Question: how is recursion different from loops? Well, you can do a lot of the same stuff with them. It's actually a pretty good question. Like in the programming language Haskell, all of the things which in any other programming language you would do with a loop, in Haskell you do it with a recursion. So if you want to do, for example, a sum function, like just add the things in a list, right? Is recursion faster than iteration? No. It's not necessarily faster. I'm not actually sure what the I'm kind of inclined to say it's probably around equivalent, but what it does is it allows you to restructure your algorithms so that your algorithms might be faster. But like if you're directly translating between recursion and the same thing, but in imperative, then, or in imperative, then you might not be getting the gains you're looking for. So let's say we've got So I've got a question: can loops replace recursion for any problem, or do some read the Java documentation. Can loops replace recursion for any problem, or do some problems require you to use recursion? To answer this question, I have to talk about a principle in programming, like a general principle of programming, called Turing completeness. So, very, very quickly and roughly, the Turing machine is it's a model for computation, like a mental model for it. If you imagine a tape with, like, I think it's forward, back, read, and write operations, then essentially what you've created is a 1-bit linear computer. And this turned out to be reasonably close to the underlying electronics. So what happened later in the development of computation as a science is that you had many different types of competing models for computation that were developed. The Turing machine was one. You also had the Lambda Calculus of Alonzo Church. You had Markov chains. You had a bunch of other ones as well. It was a fairly famous result, I think in the 70s, that it has been proven to be true that any program that is expressible in one of these models of computation is expressible in all of the other models of computation. So anything you can do in Lambda Calculus, you can do with a Turing machine. This is a concept in computer science called Turing Equivalency. So we talk about programming languages as to whether they're Turing equivalent or Turing complete, i.e., can they do everything that a Turing machine can do? Because if they can, then you can literally express in that language any program that's been written in any other Turing complete language, right? So, with respect to recursion, what that means is anything that you can do in recursion, you can do in loops as well. And anything you can do in loops, you can do in recursion, because they're isomorphic constructs in a sense. So yes, anything you can do in a loop, you can do in a recursion, and vice versa. The issue, though, is that sometimes a problem defines itself very well using an inductive definition, such as the one that we've been doing with Factorial. When your program, when the structure of the data and the structure of the algorithm that you want to use on that data suggests recursion, you probably are going to have an easier time using recursion than using loops, or iteratively. So let me catch up on these. So for the factorial example with the base case would be anything that the function would not be called for. Well, actually, no. So the thing is, it's like there are inputs for which factorial isn't defined here, right? Like if you enter a negative number in here, there's no case that handles. Well, actually, yes. So what do you think is going to happen if we enter a negative number into this factorial function? Just out of curiosity, eh? Actually, you know what? Let's do the one on the previous slide just because it's a little shorter. Copy. So, factorial of -1. Again, see, we hit a recursion error. Maximum recursion depth exceeded in comparison. So the issue is, if you miss the base case of 0, then you just keep like trying to calculate. Basically, every factorial of a negative number depends on a larger negative number, and you never hit a case where it doesn't require another call to factorial, so it just goes forever. So if it can be done in either way, loop or recursion, and they are similar in speed, why use one or the other? Again, it comes down to the structure of the algorithm. Sometimes the algorithm naturally suggests a recursive solution. This is often the case with more advanced data structures. So in a linear data structure, it's very it's very straightforward. We're getting way off topic, but we're learning, so there you go. So there's a thing in programming which is called a tree, right? So if you have a tree, then you have a bunch of nodes, and these nodes are connected by branches, basically. So this is what a tree looks like in, you know, it's a directed, not necessarily directed, acyclic graph. So if you have an algorithm that applies itself to a tree structure, you can start here, right, and call whatever you do to this node recursively on its child nodes, right? Both of these children, as long as whatever you're calling on them is sufficiently robust that can handle, for example, the fact this only has one child, and carry it, as long as it covers all of the cases, then you call the same function on every element of this node, but you do so recursively, right? This is a recursion, even though it's, because in order to get the result, like you can imagine if this was numbers, right? If this was like 7, 3, 4, and 8, and 2, and 9, in my horrible MS Paint speak, in order to sum all of the numbers in this structure, you would have to go down the list, get the sums of each of the child nodes, right? The sum of any specific node with no children would just be the number of that on that node, and then you, in that manner, would pass that data up to the top node, and that would be your result. So that's how you would acquire data from a structure that naturally suggests recursion. Hopefully that gives some sort of idea. So yes, good questions though, very good questions. So here's another technical point. Every time we recurse, that is to say we call something, the interpreter creates a new scope for the variables in the function. So that's a very small, that could use an example, I'd say. So in this previous example, right, so you remember how I did the thing with the brackets, brackets inside brackets inside brackets inside brackets? I wasn't just doing that. Like, that's when you do recursion, you're also creating nested layers of scoping in the same way that we were talking about earlier in the slides. So you can use that or not. Your choice. So recursion is a natural technique for solving problems with an inductive structure. But depending on the structure of the problem, recursion can be inefficient. So this is a big example. We'll go over the definition of this, and we'll see how much time we have for it before the break. At this rate, I don't know if I'm going to be able to get through everything in 3 hours. We might have to just, I don't know. I'd like to just, I'd like to stay on schedule. So maybe we'll do an extra hour or something, or however long it takes. So, Fibonacci. This is the Fibonacci sequence defined recursively. So, Fibonacci number of n is equal to the Fibonacci number of n minus 1 plus the Fibonacci number of n minus 2. Or 1 if n is equal to 0 or 1. Our most direct translation of that into Python code is as follows. Def fib n. If n is equal to 0 or n is equal to 1, return 1. Else, return fib n minus 1 plus fib n minus 2. So, let's try it. Copy. Give me a new cell. So, let's see here. Fib 4 is 5. Fib 5 is 8. Fib 6 is 13. Fib 10, 89. Fib 20. 50. Uh-oh. It's taking a while. It's taking a while. So this is a practical. We're just going to let that crunch itself out a little bit. I might actually hit the recursion limit. I'm not sure. So this is an inefficient algorithm. And we're going to spend the next few slides explaining why specifically this is an inefficient algorithm. So this is a algorithm. This is a modification to the algorithm that will tell you how many times, levels of recursion that we have for this Fibonacci. But I'll just, it's in the interest of keeping things moving. Here's what's going on here, right? So if you call fib 4, that requires fib 3 and fib 2. Fib 2 requires 1 and 0. Those are both base cases. Fib 3 requires 2 and 1, and fib 2 requires 1 and 2. The problem that we have is that this Fibonacci number does this for every single number. Every single time fib 4 is called, it generates this entire structure of calls in order to answer that question. Fib 5 requires 4 and 3, so you get a duplicate of this and a duplicate of that. So the more and the more and the more of the numbers that you add there, the more calls to Fibonacci you need. And as you can see, it reaches a point where it just goes for a very long time. We'll see if this terminates before the lecture does. So, I hope my computer doesn't start heating up. Anyway. So, using this counter, if we measure the number of times fib 4 executes, we get 9 executions. 1, 2, 3, 4, 5, 6, 7, 8, 9. For fib 6, we get 25. Fib 8 is 67. Fib 10, 177. You might recognize this as an exponential growth. This is bad. Generally speaking, we like to avoid exponential growth in program runtime whenever we can, especially if it's based on the number that's given into a function and not the number of inputs given into a function. So, a purely recursive solution to computing the Fibonacci sequence is inefficient because it has to recompute the same value many times. A more advanced technique, called dynamic programming, remembers intermediate solutions to save on recursion. So, with respect to this, if we keep a database of what the value containing all of the values that have been calculated, fib 2 for instance, fib 3 for instance, then we can vastly decrease, the amount of time that it takes to execute this function, which is a thing that we're going to do after the break. Cha. Blammo! Or I could write something myself. Like, gross. I like synthwave music, but it's also dead simple. I can't imagine, like, it's too difficult, as long as you know what software to use. But, you know, that probably is what differentiates good synth music from bad synth music, or synthwave. I think it's mostly, like, just finding interesting samples. But anyway, getting back to the Fibonacci thing. I've decided that, like, if we have to run this for an extra 10 or 20 minutes at the end, then so be it. I ask your indulgence. Anybody who can't catch it, who has to go at 8:30, well, that's everybody actually because of the tutorial, then you can just sort of watch it afterwards. I have a hair on my tongue. It's so annoying. Anyway. Got it! Arr, you bastard. There we go. So, the YouTube audio library has a lot of free music I can use. I'll have to look into it. So, anyway. As you might have figured out, we have a problem. Infinite recursion can occur in the same way that infinite loops can. If you miss the base case, or the base case accidentally gets bypassed, then it'll just recurse off into the distance forever. So, a modification that you can make in order to make things safer is actually very simple. Simple but important. Let's go back to this guy. If instead of having an else case here, we do else if n is greater than 0, rather than just doing all of the else cases, and then else return, and this is something we haven't covered yet, but raise value error, which just causes an exception. So, like, for example, if you try to... Really? That should have had an... Oh, yeah, because it's still working on this stupid thing. I'm going to stop you. There we go. There. See? We create that value error whenever we get invalid input. Anywho, yeah, I do think some music during the break would be very, very nice. Anyway, where was I? Oh, yes. So, just be careful of infinite recursion. It can happen to you. Generally speaking, it's not as big a issue inside of the Python environment as an infinite loop, because it will eventually end when it hits its recursion limit. But that being said, the Fib50 example still hadn't terminated, had it? And that thing was running a good 15 minutes. Well, actually, I killed it so that the other one would run. So, yes. So you can imagine in this particular... Oh my god. My brother is texting me. Sorry, dude. Streaming. Right now. ... Send. I don't care about your cupboards right now. I'm trying to teach people recursion! His cupboards, I think he painted them. Anyway, yeah, the latency is probably picking up. Sometimes I think the way that they... fix the buffering issue by introducing more latency, but anyway. So, in this particular case, you can see that if we've got n-1 and n-3, n-3 will actually skip one of these two cases, for 1/3 of the inputs, right? So you can get, 1/3 of the time the thing crashes, which is terrible. You never want that. So just be careful with it. So, going back to stuff that we covered in like the first lectures, with respect to measuring efficiency, we've got a few approaches that we can take. Basically theoretical and practical. In terms of the theory, you can generally, this means taking a look at the code and estimating how much runtime or memory it takes based on an analysis of the code. Whereas practical, you actually run the thing and see how long it takes or how much memory it takes. So, practical runtimes for our recursive Fibonacci algorithm are, well, you can see that they increase rather exponentially here. For every every time n goes up by 5, you can see our runtime increases by just shy of a factor of 10, which is bad. A factor of 10, not by 5, right? So you can see if we graph this that what we have is an exponential curve. Exponential runtimes are, generally speaking, universally despised. So let's introduce a thing called memoization. Let's try to implement this. So the idea is that we keep a record of all of the previous Fibonacci numbers that we've been using. This is a very useful and important example, so we're going to go through it in some detail. So we are going to, and this is kind of a, my goodness. We're going to create a dictionary. It's now let's not call it that, because then it'll be confused with an actual dictionary. Let's call it the memo. This will be an empty list. Well, actually, you know what? A dictionary also works. We'll do a dictionary version, just for fun. So, the thing that we want to do is, the first thing that we, basically, before we take the recursive step, we want to see if the thing that we're trying to get is in the dictionary or not. So, and we want to do this for both of the Fibonacci numbers that we're trying to get. So, if fib if n-1 is in the keys dict.keys, then let's have a intermediate variable called f1 is equal to dict indexed at n-1. Else, cats are playing with the door. It's so cute. F1 is equal to basically you want to add it to the dictionary and then use it. Dict n minus 1 is equal to fib of n minus 1, and then f1 is equal to this thing that we just wrote to. So basically the idea is we're taking this recursive call out of the return statement and we are guarding it behind this if statement that checks to see if it's in the dictionary or not. If it is in the dictionary, then we use the dictionary value, and instead, or if it's not in the dictionary, then we put it in the dictionary and then also still use that dictionary value. So, and then if you just do the same thing with n minus 2, there you go. I call that F2. Then this should be a memoized version. Does it compile? It compiles. Fib 4. Does it work? It does. 6. There you go. And you know that fib 50 example? Well, you know, let's see if we can work our way up there rather than just assuming we get it the first time. Oh-ho. Oh! Aha! You see that fib 50 thing that was literally going to take forever to calculate this number? Well, you see, we just processed that in a very generously small fraction of a second. And in fact, we could probably go, yep, pretty damn fast. So, haha. Okay, maybe that was hubris. I apologize. That's also hubris. That's also hubris. Okay, so in practical terms, maybe 6. Okay, 6 still works. 7. 8. Oh-ho. 9. Well, anyway. There we go. So you can see that it actually matters how efficient your algorithm is if you learn nothing else. So this is the version that exists in the slides. Yeah, so you don't actually have to use the intermediate variable that I was using, but you know, whatever. Also, they are doing the cool thing of passing this memo on. So in this example, I was kind of doing the thing that I advised people not do, and using the memo as or the dictionary as a global variable. Incidentally, the reason that you're able to write to it as well as read from it is because when you create when all of these formal parameters are assigned to that, they're assigned it they are assigned. It's by assignment. So what we're dealing with are many nested pointers to the original data structure. So that's why all of these work. But we can do it a little more fancily. We can do it a little better. So we can say dictionary with a default parameter of an empty list or an empty dictionary, which should have the same effect. And it also means that dictionary is not accessible outside the function. I hope so. Or it is. Whatever. It's not like I care. Interesting. Oh, okay, the reason it's doing that is because of the way that the Jupyter notebooks work. it keeps loaded all of the previous boxes that you've run. So this is actually the old version of dictionary that's used right here. Like if I did this for 10, it would have values for numbers that have not been calculated this run, right? So anyway, so that's how to do memoization. This is a cool technique. You can also, another word for this, a more general word for this, is caching. Caching is the idea of saving the results of calculations that are long so that you can refer to the cache for those values rather than having to recalculate them each time. And this is a very common thing that is done in computing because it's a good technique. As you can see, caching works. Caching, good. Love caching. Caching, 10 out of 10. Would cache again. So, you can see that with the revision of our Fibonacci algorithm, we have transformed our exponential curve into a linear curve. Now, obviously a linear curve is a way more desirable state of affairs than a exponential curve, because with an exponential curve, you will eventually hit some hard limit of like, well, the last one took 50 minutes to execute. The next one's going to, for one more, or 60 minutes to execute. Let's just do whole hours. If n takes an hour to execute, n plus 1 might take 2. N plus 2 might take 4 hours. N plus 3 might take 8 hours additional. And et cetera, et cetera, et cetera. It'll go up like that. So, bad. Just not fun. But linear, nice, cool. Everybody wants to be a linear runtime curve. So anyway, if there are any questions about that, please take a moment. I'm gonna take a bit of a moment to answer any questions that you might have about that in the chat. So the question, is there a good example of things that cannot be solved via recursion? I assume you mean. I don't know. Hardware stuff. It would be hard to do hardware stuff with recursion. But that's kind of that's kind of a non-answer. Is there any way to make a function with runtime curve that it's flat so it takes the same amount of time regardless of the input? Generally speaking, depends. Like this is operating on the size of n. You can easily imagine a function that has a flat runtime with respect to whatever value n has, right? That being said, the normal the normal situation for runtimes is data structures, like linear or otherwise. So when you increase the number of things in a list you're processing, that increases the number of times you have to process stuff, basically. Like you can get actually, you're kind of anticipating the next example a little bit, because we're going to talk about a algorithm that can be made to be more efficient than a linear curve. But generally speaking, you can always expect the amount of time it takes to process something to increase with the complexity of the thing you're trying to process. That's kind of a that's almost as fundamental as something like laws of thermodynamics, or like the law of energy conservation. The more shit you have to shovel, the longer it takes to shovel it. Pardon my French. So, can we make the runtime even less? For this particular example, well, understand that the runtime, although we have used the trade-off here, right? We have like drastically improved the runtime, but the price that we've paid for it is we have we're consuming a lot of memory to do so, right? However, sometimes that's a trade-off that is useful. So you could do a linear version, runtime version of Fibonacci without using all that memory. And the way to do that would be to use a loop and keep track of the previous two loop iterations. Yeah. To Saleh's questions, so to linearize in the time, you just define large values into a dictionary. It doesn't work in all cases, but in this particular example, it does work, yes. Depends on how you design the algorithm. Question, do you mind explaining how the meme works? The memo? I don't think anybody on this planet is capable of explaining how memes work. But yeah, so the memo works by keeping track of the previous values, right? Every time before we use a value, we look to see if it's inside of the dictionary. If it's inside of the dictionary, then we just refer to that dictionary value. If not, we insert it into the dictionary. So over time, your dictionary is populated with all of the values that you need to know. And if you take a look at this, you'll notice that this is actually the Fibonacci sequence, fully iterated. So hopefully that's some kind of an explanation. I feel like my voice is starting to go a little bit. Search algorithm. So, let's propose a problem. Let's suppose we have a sequence of length n, so like a list or something, and we want to know if a particular element is in the sequence or not. How many entries do we have to check in order to know if the thing is or is not in a list? So, the answer to this, if the sequence is not organized in any way, you can make no assumptions about the values, then you literally have to check every single element in the list, because the one you're looking for could be any one of them. However, if the list is sorted, then perhaps we can do better. And this is sorted, not sorted, S-O-R-D-I-D. That would be not good. So, with respect to searching, unstructured search is just the first case that we talked about. It's just you go through and you check everything. And I know that in does this, but just, let me have my lecture, please. I know that in does this. So if we have a list, which contains some random assortment of values, right? Then for elements, let's say we def search, we are searching list for element for thing in L. If thing is equal to E, return true. And if none of that ever works out, return false. Memes are like recursion. You start with a joke input, the template changes every time for the same joke iteration. It eventually becomes unfunny. Stack Overflow. It's programmer humor. You should make a meme. Haha. True facts. So, if we, let's just clean this up a little bit. There we go. So, if we search L for the element 10, we fail to find it. However, if we look for 7, it is there. Unstructured search. We can do better. Ooh. So, the idea is, if it's random, then there's nothing really you can do about it. But what if it's sorted? I think this works. Sort. Dot sort. Is that how it works? No. Oh, maybe L dot sort. And then show me L. Yeah, there we go. So if our data, then there are certain assumptions that we can make. Specifically, things that are smaller are to one side, and things that are bigger are to the other side. I have to correct, boomers are not the base case, because each generation of human beings is a recursive iteration on the previous one. So the boomers also had parents, is what I'm trying to say, and they were their parents were probably the same degree of uncool to them as they are to us now, except their boomers are like our grandparents, I guess. I don't know. Depends. Anyway. So, here's the, so that we did. Unstructured search is sometimes called linear search because it goes through the sequence in a linear fashion, and its runtime is a linear function of the list size. There you go. So, if the search is sorted, then we can make use of this organization to make the job easier. So, let's assume that the list is sorted in increasing order. And here's a description of the algorithm. We look at the entry in the middle of the list. If that entry is less than the one we're looking for, then we know that the one we're looking for has to be higher than it. If that entry is greater than the one we're looking for, then we know that the entry has to be on the other side of the array. And if that entry is the one we're looking for, then we can just exit. So, let's see what that looks like in code. Def. Binary search. Just so you know, I have occasionally used this example, just plucked it straight for an exam question in the past. For. No. If. And how do you get the middle element of an array? Well, you say L at length of L, integer divide by 2. That's how you get it, sir. If that is equal to the thing we're looking for, then return true. else. If this thing is greater than the thing we're looking for, then we know, so if the middle element is greater than the one we're looking for, then we know that the element we're looking for has to be in the smaller half of the list, right? So we return binary search, recursion, on a new list, looking for the same element E. That new list is, and we're going to use list slicing from the beginning of the list to length of L divide by 2, integer divide by 2. There you go. And else, because the only thing left is the case where where E is greater than this bit here, right? But we're just not going to put that. We're just going to use an else. We want to perform binary search on the other half of the list. So we want to go from length of L divided by 2 plus 1 to the end of the list. Yeah. So that will hopefully eventually result in goodness. However, there's a crucial thing that we have forgotten since we're doing recursion. The base case. So, what is the base case for binary search? Well, if your array only has one thing in it, right, then you can always decide whether that one thing is the thing you're looking for or not. However, my Haskell fans in the crowd will instinctively gravitate to if L is equal to an empty list, because it also works in the case where L is an empty list. So obviously, some element E cannot be in a list that contains nothing, so this is still true. And we get the added advantage of being able to handle as input people giving us an empty list, which is generally speaking a good thing to be able to handle. So let's see how it works. Binary search L 40. And just for fun, I'm going to put some print statements in. So print L we're going to just do that. L is equal to that. Print E is equal to whatever E is. And yeah, that'll do. Or no, we don't need to print E each time. That's dumb. Just need to print L. So let's see. So if we're searching for 40, 3, which is the middle element, is less, or it doesn't, it looks like it's taking this one. This is less than the number we're looking for, so we look in the top half. There's the top half. We look at this. Da-da-da. That's 8. 8, we're still there. This is the slice on nothing. Like if you're trying to slice off the end of nothing, or if off the end of something and it's nothing, it actually gives you an empty list at the end of it. So we end up with false. This is good. So what happens if we find something we're actually looking for? Let's say we wanted to find 0. Same thing. I should pick something in the middle though, shouldn't I? Pick 5. There we go. So you can see it first narrows the window to this, then it narrows the window to this, then it narrows it to that, then it finds 5, and it returns true. So there you go. This algorithm is called binary search. And this is another visualization of a possible execution for it. So this top bit is number of elements, and this is the way that the list is narrowed down over time, with the middle element highlighted. So, searching for 33, we find 22 in the middle. It's got to be higher than that, so we take the top half of the list. Then we have 43, so it's got to be in the bottom. 29, got to be in the top. 32. 32 is not 33, so we know that that's all the things I said. That's not equal to our target. So here is binary search using recursion. This is roughly equivalent to the thing that I did on in Jupyter. However, they have just taken a different step here in that mid is calculated beforehand and used a few times rather than being repeated through, which is just a little bit wordy. And also, the if length is equal to 1 case doesn't actually need to be included, as it turns out. You know what? I think I might finish on time anyway. So, binary search using recursion is much, much faster because it only has to compare it. It doesn't have to look at the entire list, right? In the previous version, every single element had to be examined. In this version, we only need to examine a small number of the elements. In fact, the number of elements that we have to examine here is approximately log base 2 of the size of the list. That's because every time you do this, you're dividing the number of elements in the list by 2, or slightly more than 2, possibly. Most of the time, actually. So, with respect to that, this is what you might consider logarithmic decay. And while the effect is maybe not as pronounced when we have, only 7 elements in the array, it takes 3 steps. Take, for example, if you had, 500 million elements, the next step down from that is 250,000 or 250 million elements. Then you eliminate 250 million cases that you have to check all in one step. So the question is, when we use the in operator, what kind of search is it? That's a good question. Python in operator algorithm. Other people have also asked this question. Interesting. So this is actually the source code for the in operator, and it appears to be written in C? So, kind of funny, maybe. So, yeah, this is totally C. They've got pointers and everything. So, just so you know, for you Haskell purists out there, the Haskell compiler is in fact written in Haskell. So, yeah, this looks like a reasonably straightforward check every element algorithm. So yeah, in uses the linear search that we talked about earlier. So binary search is more efficient than in. Haha, there you go. I have answered your question in a manner which is hopefully robust. So, yes. So, This is good. However, it could still be better. This version that we've got here, when we use the slicing operator. Yes, Haskell gang. Imagine having side effects. Haskell gang. So when you are creating these new lists using slicing, what you are actually in fact doing, remember that this is a non-mutating operator, which means it generates a new version of this list in memory every time it's used, right? And since this is a recursion, all of the old lists are not being deleted, right? They're waiting on. They're not being deallocated. So you can see we've got +1 instead of slicing. That's the equivalency to the slicing operation. So with respect to that, I don't really technically need this helper function, because you could just rate all of this at the search 3 level, just include high and low with default arguments. That would be fine. Like if you default argumented 0, well, I don't know if at length of L you can do that. Can you do default arguments which have the values of previous? I don't know. That's an interesting. Oh. Does that actually work? Does the pressing F thing actually work? Like, huh. Well, so the issue with the stream is, I can't imagine how VPNing through Mac would help in any way whatsoever. I would still be subject to whatever local lag I'm experiencing right now, and then I would also still have to go through McMaster and all of that. Although McMaster has a very good internet connection, but this is, I think, just a problem with residential. I think this is just a problem with residential internet connections, to be honest with you. Oh, is it? Okay. Oh, press F to pay respects. That's the meme. Okay. It's like saying RIP but shorter, which means that it's now the new RIP, I guess. Okay. Anyway, yep. I don't get all the memes, I'm going to admit. So anyway, the thing I was saying, with this helper function, you don't actually necessarily need to define a helper function inside here, because high and low could, in theory, be made default arguments with these as defaults, considering this is the only way in which search 3 helper is even used. That said, I'm not actually sure if you can you can make a default argument involve one of the arguments that's higher up in the arg list. Maybe, I'm not sure, but there you go. Anyway, so that's binary search. This is a good one. Yes, and functions can be local to functions. So, in Python, so new topic, functions as objects. This should be very familiar for the Haskell crowd. Imagine things not being functions. Haskell crowd, or Haskell gang. In Python, functions are first-class objects. We can use functions like objects of other types. In particular, we can pass functions as arguments to functions. We can pass functions as arguments to functions. That basically makes it Haskell. I'm kidding, of course. This is why we say Python can behave like a functional programming language with, sorry, oh my goodness, that was involuntary air sarcasm quotes from my Haskell programming fingers. So Python is a multi-paradigm language, which basically means they steal from other languages who have better ideas, i.e. Haskell and its functionalness, and this is an element of that. So, for example, map. Map is a cool function. Basically, if you have a list of things, it will apply whatever function you give it to that list of things, right? Victorious! Triumphant return. Good lord. That's like, confused. I'm sorry I confused you. Nick the Evil Scientist is like the account that I'm logged into on my phone. They're the same person. That's my alter ego, like Batman. Batman and Peter Parker. Anyway, sorry about that, guys. I actually had to run down to the basement and bump the router, and that seems to have fixed things. I apologize profusely. I'll try to not have that ever happen again. Although, completely honestly, I have no idea how I would prevent such a thing from happening because, holy shoot, I have no idea what caused it in the first place. So, yeah, where were we? It's kind of dubious, like, how much of this was actually, recorded, you know? Like, how much did we lose? Come on. Well, anyway. So, chat, could you please give me some indication of what the last thing that was audible that I said was? And Mars Lettuce, if you're going to pretend to be a Python interpreter, you can at least put the 3 carets in. The second last slide. Okay, thank you. Boy, the latency's pretty good. Crazy. Anyway. Oh my god, no. Come on, Dad. You know I'm lecturing right now. Good lord. Let's just get through these 2 slides. Just 2 slides, folks. Just 2 slides. Okay, so, map. Map is like the quintessential example for passing a function into a function as an argument. What map does is it applies it applies whatever function you are mapping, which in this case is f, to all of the elements of the thing that's the first argument, in this case a list, although because we are using a for loop to do this, and a... Oh my god. They're actually... Pardon me for a second. Honey? I think my folks are at the door. Would you mind? I'm trying to finish off the lecture. I'm sorry. Oh my god. That's not social distancing. Welcome to the worst end of a lecture ever. Anyway, if you take, if you apply some function, if you put a function in here, basically it takes that function and all right, I'll sign it. I'll sign it right. I hope. Oh my freaking god! I hope that this was important enough. I have to sign the back, right? I think. Could you ask him if I have to sign the back? Oh my god. we're going to have words later. So, yeah. Thank you. If you take a function and you put it in as an argument to the function, you can treat it like a function inside of the function that you've passed it into. The function behaves like an alias in that this is now whatever function you pass to it, right? It could be math.cos, it could be anything that you put in here. So, yes. So that's that slide. We can do it with cos, we can do it with fib, we can do it with whatever. You can also create anonymous functions. Anonymous functions are functions that you create in place. So, for example, maybe when you use your map function, you don't want to go to the trouble of, like, if you want to do something simple, like just add 3 to every element, right? Maybe you don't want to go through all the trouble of creating a whole function for something that's so simple. Excuse me. So you can actually create functions in line using Lambda. Lambda refers to the Lambda Calculus of previous. Don't worry, I'm never going to test you on this. So basically, when you have a Lambda expression, you have some variable names and you have an expression, right? And the variable names, whatever variables you specify, get extracted out of that expression and made into arguments. So Lambda, just for example, if you have Lambda x plus 3, and then you apply 7 to that, I think that should work. Yeah, you get 10, right? This creates a function, all in line, very compact notation. But the interesting thing that you can do with that is you can throw it in to map, and it'll work in there too. But not if you do that. And you can do this with multiple arguments. So there you go. Anonymous functions. They're called anonymous because they don't have names, basically. Yeah. So anyway, that's the end of the presentation. Sorry about the last 20 minutes or so. I have no idea what was happening, but I'll see if anybody has questions, if I can get connected to the chat again. Good Lord. What a... Oh my goodness. Okay. Memes. No, it wasn't over the cupboards. They needed me to sign a check. Okay. Oh my God. Anyway, so let's end the stream from hell. This shall forever in my mind be known as Hell Stream. Thank you very much for your time and attention. So thanks. Good luck on the test.